Alright, these are the notes for LT1 and the light unit. So this is immediately following the kind of the basics of waves and the sound unit. So we're now in light, and the purpose of LT1 is to rank waves of the electromagnetic spectrum by energy, wavelength, and frequency. I apologize, my voice is recovering from strep throat here, so my voice is a little shady today. But this is not a memorization target at all. The biggest thing is I'm going to give you a picture of the electromagnetic spectrum. You need to understand trends. So you need to understand as you move to the right what happens to the energy of the waves, what happens to wavelength, what happens to frequency, what are some uses of these waves within the electromagnetic spectrum. So the notes are very different. If you are not in class, and that's why you are watching this, you will need to pick up a blank template like this from me. And during the notes, I'm not going to rewrite all this. I'm just going to show you, so you'll need to pause me as you're copying this down so that you can copy these onto your blank template, which again, you may just need to pick up on me when you get into class. All right, so what we're actually going to put onto notebook paper here, electromagnetic. Okay, how do we get this? And now we're talking any type of light, and light doesn't have to be just visible light, okay, but any wave within the electromagnetic spectrum is created the same way. So we're going to start with our little picture first here. And let's say we have an electron vibrating up and down. If that electron jiggles up and down, it will create a magnetic field that is exerted perpendicular to it. Okay, so at a right angle to it. And you may remember when we made electromagnets back in the electricity unit, how we passed a current through a wire. So we moved electrons, and you created those the invisible magnetic field lines, which caused your compass needle to go crazy as you went around it. Okay, that's really no different than what's happening here. So an electron jiggles, it creates a magnetic field. Now the unique part is that this magnetic field will cause other electrons to jiggle. And in turn, they're going to create, I'm just going to call it MF, more of a magnetic field. So this is a huge, huge difference between sound waves and light waves. Remember how sound, think back to the domino lab, a sound needs a medium. And if that medium is close together, sound travels fast. Light is totally different here, all right? Light actually prefers not to have a medium. So sunlight, for example, coming through the vacuum of space, it is when you hear somebody refer to the speed of light, that is when there is no medium involved. Light travels the fastest in the absence of space. Because electrons move, they create a magnetic field. That causes more to move, and we say that they propagate. All right, so we're going to go over here now. And so what we get is vibrating electric and magnetic fields regenerate to propagate. That means to move something. Which means to move a light wave. Okay, so the vibrating electric particles vibrate, create a magnetic field, causes other ones to vibrate, and essentially they just kind of snake through space. So we're talking about these types of waves now. And it happens in places other than space, so don't let me mess with you there. But we are talking about transverse waves. If you need review on that, go back to LT1 in our last unit, which was kind of like basic wave properties. And remind yourself about crests and troughs and wavelengths and all that. Now, we're not going to put every single detail in our notebooks about the EM spectrum. Okay, but there's some trends we need to know. And I'm just going to put the extremes in here. Hopefully, we recall, because we talked about this before, the lowest end, the lowest energy end are radio waves. The highest energy end, so greatest energy, are gamma waves. Okay, lots of uses here, but for right now, radio waves, gamma waves. Make sure we don't think radio waves are sound waves. Radio waves are like what your cell phone communicates with, like the antenna, the signal it's getting, the signal to an FM station, radio station, something like that. All right, that's radio. So we know a trend is as you go to the right, we see more energy. Okay, it increases in energy. Also, as we go towards this gamma ray end of the spectrum, we see a higher frequency. So it's like if you were able to feel these waves hitting you, which we don't, but if you could, you would feel more crests hitting you in a certain amount of time. Okay, so as you go here towards gamma, lots more of these crests would pass a point in a certain amount of time. So if they have more energy because of this higher frequency, that must mean that wavelengths would actually increase as you go the opposite way. So the distance between crests, or the distance between troughs, that increases as we shift towards the radio end of the frequency. Okay, they get farther apart, so that would make it a lower frequency, a longer wavelength wave. Now, you're probably able to keep up with this without much problem, but I worry on this next part. Make sure you pause me. We go to a NASA website, which you see these links on Moodle, and you have this template, hopefully. If you don't have this template, wait till you get it from me, then start the video then. But this is just what we just did in notes. We know that energy and frequency increase as we go to the right. Wavelength increases as we go to the left. So what we're going to do is just start here at the radio wave frequency. 19 centimeters at 12 million meters is your typical wavelength. So huge variation. Many things can produce these types of waves. If we're talking celestial objects, so things outside of the Earth, stars, space objects, perhaps things within the Earth or on the Earth, things that we use every day. Could be a cell phone, could be a radio tower. Detectors are things that would recognize these waves and receive them. So like antennas, you have a built-in antenna within your cell phone. Radio telescopes, huge dishes pointed at the sky that receive radio signal. All right, that would be a radio telescope. What do we use them for?